Mm. Okay, so first, thanks a lot, Mariana, Alvaro, and Nico for the invitation to give a talk in this very nice conference. So today, in accordance with the title of the workshop, I will tell you something about deconstruction, at least partially, of the heterotic flux landscape. So this is based on work which is in progress, who is Ilarion Melnikov, Nation, that you all know very well, and Jan Proto, who is currently my student, and by the way, who is on the postdoc market and who is doing really very well. Okay, let me start with an introduction. So I thought before the conference that heterotic tricks deserved to be motivated, because after all, it was something that was at the center of focus in the 80s, so it looks a little bit old-fashioned now. But we have seen in the very nice talks of Hector and Rui that there are still many interesting things and things that we didn't expect to find in this context, because it has a very rich structure. Okay, so in the 80s, people were interested in finding a phenomenological model from string theory by looking at heterotic compactification on Calabi-Yau manifolds with some Hermitian-Young-Mills gauge bundle, and as you know, this is plagued with the problem of moduli, and so even in this nice and old context of heterotic strings, there is still room for fluxes, and this is what I will talk about today. And it's a little bit different than other type of flux compactification for several reasons, and I will first give a very short review about the feature. So these are just the generic heterotic compactification in 4D that can be understood geometrically, so they are worthwhile discussing. And but the problem is that we don't have many classification tools for them. Why? Because we lack all the nice theorems that we have for Kähler geometry, the Yau theorems that tell us that there is a Calabi-Yau metric, which is Ricci flat, the Donaldson-Uhlenbeck-Yau theorem that tells you that under certain conditions you have a connection on a gauge bundle that respects Hermitian-Young-Mills, so we don't have anything of this sort in this case, because the geometry is generically non-Kähler. So this is the first characteristic. So we know only, at least for minimal supersymmetry, very little of it. And also because the way the free-form flux is implemented in the equation, you will see, there are always cycles in the geometry that are string scale. So it's not so obvious that you can really make more sense of supergravity in this context. But fortunately, because it's heterotic, you only have flux for the free-form H and for the gauge field. So in principle, at least, you could use the worldsheet method and say that you have some 0,2 superconformal field theory on the worldsheet that you could relate to some nonlinear sigma model with some target space of this sort. Okay, so there is essentially, even if this object at least is known for years, one class of solution that has been constructed so far, not more, that are principal T2 bundles over K3 surfaces. So they were originally motivated from M-theory duals, but there have been a lot of work about this from that period, and they preserve at least 4 supercharges. And the point is that, unlike what we expect for general heterotic flux compactification, the torus part, the fiber, is small, string size, but the K3 base can be as large as you like. Okay. So there are generally 4 supercharges, but there is a subcase that I will discuss in more detail, which preserves actually 8 supercharges. And in this case, it's even believed this is a paper of Ilarion, Ruben, and Stephen Steisen, that they exhaust just all possibilities of 8 supercharges compactification of heterotic strings, which includes, of course, the trivial fibration, which is just K3 times T2. So I told you that there are potentially worldsheet model. In this case of model with 8 supercharges, they are not properly superconformal field theory, but UV completion of what we believe are nonlinear sigma model on those geometry, which are kind of variants of the usual gauge linear sigma model. And what's nice with those type of tools is that if you have quantities that are protected by supersymmetry, you could compute them exactly, and this is what we did a few years ago in order to get, for instance, the exact form of the threshold correction in this torsional background. So one point of view that Ruben likes a lot is saying that because the base can be as large as you want, you can just decompactify the theory and view the theory as a compactification of a certain 8-dimensional theory, in which of course all the Narine dualities that we have heard about already today plays an important role. Okay, so the original goal was to explore in more detail the detail of the topological details that could enlarge a bit our understanding of this model, especially for 8 superchargers, because we think that they are just the whole landscape of compactification. But in the meantime, probably because I agreed to give this talk and the course of the workshop had to play a role, and so we discovered that instead of enlarging, we just maybe killed a large part of this moduli space for a reason that I will explain. And this will be the main point of this talk, just to tell you that there are ways to relate flux compactification to some that are non-fluxed. Okay, so I will start with some review of facts that are probably well known of some of you, or maybe many of you, about the geometry of topology of those heterotic compactification. After, I will make a bridge with things that we have heard already today in the previous talks, which are Narine lattices and some things that we didn't hear about, which are rational CFTs that play an unexpected role in this story. And after, we will see what things can happen in those flux vacua using this presentation of the fluxes. Okay, let's start with a review of known and old facts. So actually, the context in which we should study those flux compactification is known for many years. So Chris and Andy told us what to look for in the 80s. So from the covariantly constant spinor for this connection with torsion on your manifold, you can extract an SU3 structure, which tells you that you have a complex manifold with a 3-0 form and a 1-1 form that obeys those conditions. The manifold is not Kähler in general, but it obeys a weaker condition that you got from the de Latino variation, which is coformally balanced. And on top of this, because it's heterotic, you have also to say something about the gauge bundle. It has the connection of the gauge bundle has to obey this equation, which is the zero slope limit of Hermitian-Mills. So this is the data of your compactification, but these things are not independent because they have to obey some anomaly constellation condition, which is the Bianchi identity, okay, which relates the exterior derivative of H, which is present whenever the space is non-Kähler, with those traces which involve the curvature of the gauge bundle and some curvature of the tangent bundle. And it turns out that if you choose the right connection on the tangent bundle in this Bianchi identity, which is a Hull connection, this and that imply the equation of motion, at least at order alpha prime. And the tricky point here is that the problem is that mathematician plays a lot with this system, but they don't answer the question that we want to answer, because they essentially try to find exact solution of this system. But the point is that both the equations are approximate. There is a well expansion at alpha prime, and the solution are also approximate. So in some sense, you have to expand both and to check whether at the right order you get what you want. So for this reason, the mathematical literature about those solution is not so helpful for physicists, and we are still back to our old friend, which is this torus vibration over K3. So now it's time to present those geometries. So you start with, of course, a K3 surface, and you pick in the cohomology, you pick two global one form on your total space of your vibration, and such that the exterior derivative of this one form of each of them correspond to some integer class in your second cohomology. So you start with two classes. You can take them independent if you want to be generic. And then you want to use them to construct your vibration. So you choose for the moment freely the moduli of your torus, a complex structure and a complexified Kähler, where B is a B field and this is the area. And so you group this one form together. And from this, you can build the SU3 structure that I mentioned before. So for instance, for the 3-0 form, you start with a 2-0 form on the K3 surface. You take the product with theta, which is holomorphic, and you get a 3-0 form. And the same for the 1-1 form, you just add this piece, which corresponds to the contribution from the torus fiber. So it's not always the case that it defines the necessary structure. You have to ensure that F, which is F1 plus tau F2, where tau is the complex structure of the torus, shouldn't have a 2-0 component. So this is what we assume, no 0-2 component, sorry. This is what we assume from now, of course, because we want supersymmetry. But there is an even refined case that you could look at if on top of it also the 2-0 form is vanishing, which means that you just have 1-1 curvature, then you preserve not only 4 but 8 supercharges, and again this is what you expect to be the generic case of 8 supercharge compactification. So then you have to tell what the bundle is. So something that obviously works is to take the connection Hermitian-Yang-Mills connection on some bundle on the base and to pull back it to the total space. But you can add something and it will play a crucial role, which looks a bit like a Wilson line. So it's linear with a constant coefficient to one of those one form on the total space. So for simplicity and because we want to exhibit some dualities, we'll assume that the bundle that we have here on the base is abelian. And otherwise, you may think that you start with a general bundle, and by moving into moduli space, you reach a point where you have abelianized everything. And this is the context that we will consider. Okay, so you still have to solve Bianchi identity. So you do have non-trivial H flux here. So it has several pieces. One that we call horizontal because it just lies on the base, and one that we call vertical because it has one leg on the fiber, and it's proportional to this piece where this is a constant metric on the torus fiber. Okay, so Bianchi is essentially given by these conditions, which tell you roughly that if your gauge bundle is too small, you don't have enough instanton number, you can compensate by the fibration essentially. So you cannot have a contribution of the fiber which is as big as you like. You just replace instantons by a contribution of the fiber. So because you have flux, you may ask whether there are quantization conditions, and here it's a bit subtle because H is not closed, and this is very important for the following. So this is something that has been obtained again by those gentlemen that I mentioned already, is that if you take the B field and you expand it again in a part with no legs on the fiber, one vertical with one leg, and a part which is just a constant B field on the torus, you can take this part, you refine it by shifting by this term, which again A should be thought as kind of Wilson line. This part transforms exactly as a connection on a line bundle, which means that you have the corresponding first class that should be quantized. So it gives you a class here, which is a combination of the omega which defines the fibration. So omega was previously this Fi over 2 pi, and it's a combination of this and the data of the torus metric. So this is a familiar metric for a Wilson line on a torus, which is not fibered, with also B field. So this has to be quantized. And it's very suggestive to put all this topological data in a single vector. Okay, so I consider these vectors. So the first two entries are the two classes that define my fibration. My two second entries are the nu I here, which are these classes that should be quantized as well. And then I have all the classes corresponding to the abelian gauge bundle. So it fills a vector of gamma 2 plus 16, understanding that each component is not an integer, it's an integral form. Okay. And the Bianchi identity can be just recast as this, where this bullet product is just a composition of the inner product on the Narine lattice with the natural product on the second cohomology lattice. Okay, so this brings out to Narine lattices because it seems that there is a very strong relation to gamma lattices, Narine lattices with this signature. So let me start by some generalities about those lattices. So I take a vector in this lattice, which is in fact the 2,2 lattice of the torus plus 2 copy of E8 of the E8 lattice, and I can expand as usual in terms of winding and momenta plus lambda, which is the weight in the E8 cross E8 lattice, and I use this metric to contract vectors. One question that you may ask in a CFT, in at least one or 2 dimension is the following. If you have a toroidal theory, under which condition you have an enlarged algebra, meaning that you have more chiral current, chiral operators than the current dx1, dx2, and so on. And for this, you need to solve the condition that, for instance, the right momentum has to vanish, and you ask that the space of solution has rank 1 or rank 2 or whatever rank you want. So in this case, if you take a T2, if you ask that P right is 0, you find that the momentum has to be related to the winding and also to the vector in E8 cross E8 in this precise way. Okay? And this, of course, is exactly the same as this condition on the quantization of the class, which means that it means 2 things. First, that the quantization condition of the heterotic flux background is equivalent to saying that at least when there are no Wilson lines, that the torus has to be a rational CFT. Why? There is no obvious reason, because we don't have a worldsheet description that would involve those extended algebras that you arise on the worldsheet. Okay, so this is the first point. The second point is that this vector here, theory that we have, we should think of it as a vector of the left lattice, which is again non-empty in this case because we have the moduli of a rational CFT. So one other thing that you can play with null lattice is to perform, of course, dualities, which are lattice automorphism, okay, and see what they mean in this context of fluxes. So among the lattice automorphisms, there are just few of them that will be of interest for us. The first one are just the generalization of the usual T-duality. You just flip winding and momenta around one circle. The second one is proper to 2 dimensions and more. It just amounts to shift the value of the B field by some integer. And the last one, which is the most interesting in this case, because it really relies on the asymmetric nature of the heterotic lattice, is the Wilson line shift, when you shift at the end of the Wilson line by some vector of gamma 8 plus gamma 8. So this is a transformation on the momenta that appear in P, but on top of this, you also have, of course, an action on the moduli themselves of the toroidal CFT. For instance, the factorized duality start from this data, radius and Wilson line, and end up with this data. And together with this, there is usually a phase that is carried by this symmetry when you act on the vertex operator of the CFT. Okay, so this was for toroidal theory. So why should we think that it's a good idea to apply this to the formal vectors that we have to define the flux background? Several reasons. First, I mean, the fiber is nowhere degenerate, so you may think that Bouchard rules apply without any obstruction. And in fact, the topological implications were studied by these people some time ago. And Ruben, with F-him, was the first, I think, to realize that you can also use other kind of duality, which are not just duality of T2, but of the whole null lattice, to change the topology of the space. And also, to be even more sure that these are valid symmetry, you can start, and this is something that I did 10 years ago, you can start with the gauge linear single model description of those background and perform duality à la Bouchard, which tell you that it's not only a symmetry of the infrared limit of the gauge linear single model, but it's an exact symmetry of the model even in the UV. Okay. And it's also, so I won't speak about the index by lack of time. So now we will just play a bit with this and see what we get and what we learn about those background. We will start with something very simple. 5-dimensional backup in the sense that you just fiber a circle over your K3 and not a T2, and to see what you get. So we have a circle bundle over K3, and in this case you just have a unique class which defines your fibration, and we write it like this: some integer h times omega p, where p is primitive in the lattice of the second cohomology. Okay, so in this case you have a single quantization condition, which tells you essentially that your radius improved by the Wilson line contribution here is quantized. It should be rational, okay? And you solve this for some integer that we call L, And so you have this value of the moduli, and you have this type of vectors that define your compactification, and this is a vector on which you can act with your dualities.
Sorry, what was
A is a Wilson line parameter. It's a vector, sorry. So one thing that was not known before also is that those spaces have a topology which is richer than expected. They are not simply connected, and pi 1 of the total space is given by the H, where H is this H which appear here in the anomaly constellation. Okay. So now we want to play a bit with the duality. The first one is the factorized duality, which is the usuality duality. It doesn't do something so spectacular, so it will just flip those two classes. And I forgot to say that I chose a model with no gauge bundle at all, which is allowed in this case because you can just, the Auwager term can be compensated only by the torus bundle. Thank you. And so you will have something which is kind of expected, but what's interesting is that the pi 1 now becomes the L instead of the H, so you just flip the integers that appear in the two entries. So the most interesting duality, and this is where the deconstruction part arises, is what we have called the unwinding duality. So it works well if we start with a model with H equal 1, which means a simply connected flux compactification of this sort. And then we do a combination of a Wilson line shift of parameter k, where k again is a vector, 16-dimensional vector, and a factorized duality. So we reach this vector together with those values of the radius and the Wilson line. And so the point is that you can always choose a vector k such as this vanishes. And when you do this, what you obtain is not a flux background, but an ordinary K3 times an S1. So you have converted your flux background into an ordinary K3 times S1 with some extra line bundle that you have here, which is not orthogonal to the Wilson line. So this is the particularity of the background. So you have K3 times S1 with a particular type of gauge bundle. Okay. So this is, in some sense, interesting. In another sense, disappointing because we have killed some of the flux background that we liked. So this was for simply connected ones. For some non-simply connected ones, things are a little bit more complicated. So when the radius is rational, it was H over L. You can start with a parent theory which is simply connected with L tilde equal LH, and you can get the theory with rational radius by doing just a shift orbifold as you would do in flat space. And when you do this, you end up with a theory which corresponds to these vectors that you like. So what you may ask is this unwinding duality that you have done in the parent theory, which is simply connected, what it becomes in this theory. You just have to trace what happens to the to the transformation that you applied after after you apply the orbifold, and you find something which looks like this, which means that you indeed have something that is like S3 times S1, which is true, but on top of this, you have an orbifold action that is not just a stupid shift orbifold like this, but something more complicated, because you combine a winding shift with a shift in the lattice E8 of EL cross E8, okay? Which means that you have the choice either to have something which is geometric but with flux, or something which has no flux, it's just K3 times S1, but quotiented by a non-geometric symmetry. And also you have many variations of this game because pi 1 is non-trivial, you can also do a CHL-like construction, and also they have duals on the unwound side, which have also non-geometric actions. Okay, so this is for the 5D case. I will very briefly say what happened in 4D. So it's almost the same, except that you have, of course, more possibilities. So you have quantization condition, as I told you, which tell you that your T2 is either rational or I would say half rational because it has chiral coherence, but it's not a fully rational theory. And now you have a vector with two primitive forms here. And you also, again, can do dualities of the same sort by combining factorized duality with Wilson line shift, such that by choosing appropriately your Wilson line shift, you can just kill the duality. So, thank you. The idea is that you start with this is an assumption. You start with any background of this type. You go to a point in the moduli space where the bundle is abelian, and then by duality you can just unwind everything. The price to pay may be to have those orbifold acting non-geometrically. Okay, this I will skip, and I will move to the conclusion. So we have found that we have some strong evidence that n equal to 2 heterotic flux background can be unwound to ordinary K3 times T2 vacua of string theory with some line bundle and certain Wilson line, which are again non-orthogonal to each other. And an important caveat of this procedure is that in many cases we end up with a non-geometric orbifold of this. So you can either view it as a caveat or something nice, because I like non-geometric background, so in some sense it's interesting to relate two different types of vacua. And along the way, we have found that there are many possibilities to construct CHA-like background because of the rich topology of those spaces. And something that I didn't discuss at all is the case of n=1 backgrounds. So they can be obtained in two ways. So either, as I mentioned in the beginning, you start with curvature of the bundle that has 2 zero piece, and this is something that we are currently studying, and it shows us everything. In particular, the 2 zero piece doesn't move under dualities, so so the vibration cannot be undone in this case. And there are also ways to construct n=1 by taking quotient of the T2 vibration over K3, which are like Borsia-Voisin Calabi-Yau threefold. And what's nice with the unwinding duality is that we may find a way to understand how to resolve those singularities without being in the non-Kähler context that we don't really handle very well. Okay, I think I should stop here, and thank you for your attention.
Thanks for the talk. Related to what was discussed before, would it mean from your conclusion that any heterotic compactification would be related to an orbifold of 10D heterotic somehow, at least connected to it?
What we say is that flux compactification with 8 supercharges can be related to orbifold of K3 times T2 compactification. But after we can move in the K3 moduli space maybe to simplify things even more.
This is what I'm asking, if I could go even that in that direction.
Yes, maybe you have to be careful, because you had quantization condition in the beginning, but in some ways are not lost after the dualities. So they still occur in the gauge bundle sector somewhere. So you have to be sure that you can do wherever you want. Because you started with something with quantization condition, you end up with something that should have somehow similar constraint. But I understand the idea you want to go to K3 times C2, then to go to the orbifold limit of K3, something like that. Yes, maybe.
Should I?
What about spaces like K3 times T4 or something like this?
You can do the same because the structure of the vibration, yes, you can.
But it's the same statement that the fluxes can always be unwound and pushed to a geometric.
We didn't study explicitly what happens, but I'm not sure qualitatively it's that different. Probably you can do similar tricks, but it's just an assumption.